Good morning, students. We are continuing with the theories and lesson 4 for bonding. Lesson 3, we looked at the valence shell electron pair repulsion theory, where we said that lone pair and shared pair arrange themselves around the central atom in space as far apart as possible in order to minimize the electrostatic force of repulsion. And we concluded that a system with the less repulsive force is always the stable system. We looked at some of the important points about this theory, where we said that lone pair occupies more space than bonded pair. We gave an example of methane, ammonia, and water. Methane had no lone pair, ammonia had one lone pair, and water had 2 lone pairs. And all of the 3 were tetrahedral. They had a structure, a tetrahedral structure. We observed that because of the 2 lone pairs in a water molecule, which are residing on oxygen, they push the bonded electrons far away from the lone pair, hence reducing the bond angle to 100 degrees and reducing the bond angle to 100, whereas that of the methane is 109. Also looked at the concept of electronegativity, where we said that when the bonded atom is more electronegative than the central atom, that atom attracts the bonded electron towards itself, reducing the stress on the central atom, electrons of the central atom. An example was phosphorus iodide, phosphorus bromide, and phosphorus chloride. And we found out that since chlorine is more electronegative than bromine, and in turn more electronegative than iodine, chlorine pulls the bonded electrons towards itself, decreasing the force of repulsion exerted by the bonded electron pair on the electrons of phosphorus, and as a result, the bond angle is less than that of phosphorus iodide, and so many others. So today we are going to look at molecular orbital theory. Also this one, the molecular orbital theory, explains the nature of the covalent bond formation on the basis of a wave function. And according to this theory, atomic orbitals having the same energy and symmetry combine to form molecular orbitals by linear combination of atomic orbitals. You can wonder what a wave mechanics or wave function is. Wave function is a mathematical function that describes or gives information about a microparticle. A microparticle can be an electron, can be a proton, you can name them. It gives information about its location in the orbital, orientation in space, probability of locating the microparticle, and its energy. Since the microparticle, you can say an electron, moves like a wave, that is why the engine value, which is the phi, this phi, is referred to as a wave function. So if we take phi A and phi B to be the wave functions of atom A and atom B, then according to linear combination of atomic orbital principle, the wave function will be wave function of atom A plus or minus the wave function of atom B. So another point to note about this theory, the molecular orbital formed by the addition of the two atomic wave function is known as the bonding molecular orbital. That is, when the signs of the two wave functions are the same, for example, the bonding molecular orbital is equivalent to the wave function of A plus the wave function of atom B. Both are positively charged. This one leads to the formation of bonding molecular orbital. Therefore, the probability of finding an electron in the bonding molecular orbital is given by this expression, which is greater by an amount of 2 wave function A times wave function B than that in either of the atomic orbital. The energy level of the bonding molecular orbital is less than that of the individual atomic orbitals, as we shall see in the others in the slides that we are going to view. Another point is the molecular orbital formed by subtraction of the two atomic orbital wave functions is known as the antibonding molecular orbital. That is, the signs of the two wave functions are different. One of the atom is positive, another one is negative. And the probability of finding an electron in the antibonding molecular orbital is less than an amount of 2 wave function of A times the wave function of B than the aid of the atomic orbitals. So the energy level of the atomic orbital, the energy level of the antibonding molecular orbital is higher than that of the individual orbitals. And the electrons present in this energy level of the antibonding molecular orbital destabilizes the molecule. Remember, we said a system with higher energy is unstable. The one with lower energy is stable. That's why electrons in the antibonding molecular orbital destabilizes the molecule because they are on a higher energy level, while those ones in bonding molecular orbital, for them stabilizes the molecule because they are at a lower energy. Another point to note, the molecular orbitals which do not take part in bonding are known as non-bonding molecular orbitals. And the energy of the non-bonding molecular orbital is equal to that of the atomic orbital. That one will be seen with an example of hydrogen fluoride. Another point is that in a molecular orbital, movement of electron is influenced by more than one nucleus, depending upon the number of atoms present in the molecule. While the atomic orbital, the movement of electron is under the influence of only one nucleus. Therefore, the atomic orbitals are monocentric, while the molecular orbitals are polycentric because they have more than one nucleus. Another point is about the stability, and the stability of the bond is expressed in terms of the bond order, which is defined as 1/2 of the difference between the number of electrons in the bonding molecular orbital and minus the number of electrons in the antibonding molecular orbital. Bond order is equal to the number of electrons in the bonding molecular orbital minus the number of electrons in the antibonding molecular orbital. The answer you get, you divide by 2. A point to note here is that the bond order may be 0, a fraction, or a positive integer. The greater the bond order, the stronger is the bond formed, and the greater is the stability of the molecule. So molecular orbitals can be represented in a molecular diagram. What are molecular orbital diagrams? These are a potential energy diagram which represent the atomic orbitals of the combining orbitals and the molecular orbitals formed. In the molecular orbital diagram, the electrons are filled according to Hund's rule or Pauling exclusive principle, whereby we fill the ones with lower energy before we go to the one with the higher energy, and the electrons must be of the opposite spin. Let us look at an example of electrons in the s orbital combining with another one in s orbital. So when the lobes are positive, they are similar, we get the sigma bonding molecular orbital. So if the atomic orbital, we have a positive and a negative, we end up with the antibonding, sigma antibonding molecular orbital. For the 2pz, we have positive combining to form the sigma overlap or sigma bonding molecular orbital. And for the positive and negative, we get the antibonding sigma overlap. When we have the 2px of atomic orbitals plus leads us to sigma overlap bonding orbital. Then if it is plus and negative, we get the antibonding, and the structure looks like that. The nature of the form of the bonding molecular orbital and antibonding molecular orbital. Let us look at the conditions for the combination of the atomic orbital. The energy of the atomic orbitals involved should be comparable. And the orbitals must overlap for the combination of the atomic orbital to take place. And the atomic orbitals should have the same symmetry about the internuclear axis. As an assignment, give 5 differences between bonding molecular orbital and antibonding molecular orbitals. And let us look at some molecular orbital diagrams for monoatomic molecules. An example is hydrogen. The hydrogen molecule is made up of 2 hydrogen, and each hydrogen has 1s with 1 electron and another 1s with 1 electron. And if the 2 combine, we get the 2 electrons. So in the molecular orbital diagram, they are drawn like this. There is increasing energy, then atomic orbital of 1 atom and an atomic orbital of another atom. In the middle, we have the molecular orbital formed. So each atom is having 1 electron in 1s, 1 electron in 1s presented in this box. When they combine, they form the molecular orbital. Let us look at the bond order. We said they are the number of electrons in the bonding molecular orbital minus the number of electrons in the antibonding molecular orbital. So this is a sigma 1s bonding molecular orbital. It has 2 electrons minus the electrons in sigma antibonding molecular orbital. We have 0. So 2 minus 0, the answer is 2. Divided by 2, we are going to get 1. Therefore, hydrogen exists and it has 1 bond. Hydrogen exists and got a single bond, and it is diamagnetic in nature. Why diamagnetic in nature? When you look at its electron in the molecular orbital, all of them are paired. We said when they are paired, the magnetic nature of that molecule is diamagnetic. When they are not paired, the magnetic nature of that molecule is paramagnetic. So for this case, hydrogen is diamagnetic because it has paired electrons. Let us look at boron molecule. Boron molecule has got 5 electrons, and another boron molecule 5 electrons. So if we put them in their respective orbitals, 1s2, 2s2, and 2p. So we have 2 electrons in the 1s orbital, 2 electrons in 2s orbital, and 1 electron in the 2p orbital. The rest are empty. Similarly, on the other side, the same. So they bond, 1 electron bond from this side, another bonds from this side to form the sigma bonding molecular orbital, then the sigma antibonding. Similarly, the s orbital, the 2s orbital do the same. We get the sigma 2s molecular orbital and the sigma antibonding. Then we have 1 electron from this coming to bond, and also this one. Since there is a space, they are empty orbitals, they don't come together. Each one occupies a different orbital to minimize the repulsion. So if we look at the bond order, we said number of electron in the bonding molecular orbital minus number of electron in antibonding molecular orbital divided by 2. How many electrons do we have in the bonding molecular orbital? We have 2 plus 2, which is 4, plus 1, 5, and 6. So it is 6 minus. What about the antibonding molecular orbital? We have 2 plus 2, which is 4. So it is 6 minus 4 over 2, which is equal to 6 minus 4 is 2 over 2. The answer is 1. Therefore, beryllium molecule exists and has got a single bond, and it is paramagnetic in nature. Why? When we go back to the molecular orbital diagram, it has an unpaired electron. The moment you say unpaired electron, the magnetic property of that molecule is paramagnetic. So is beryllium molecule. As an assignment, draw the molecular orbital diagram of neon molecule, oxygen molecule, nitrogen molecule, and calculate the bond order. Comment on their existence, number of bonds, and magnetic properties. Now let us look at the molecular orbital diagrams for a heteroatomic molecule. An example is nitrogen monoxide. The molecular orbital diagram of a heteroatomic molecule is not symmetrical. Usually, the energy levels of a more electronegative atom is slightly lower than that of the less electronegative atom. When we look at the example of a heteroatomic molecule like a nitrogen monoxide, oxygen is more electronegative than nitrogen. So when we go to the molecular orbital energy diagram, it will show that the molecular orbital diagram for oxygen, it's at a lower energy than nitrogen. And it looks like this. This is the atomic orbit of nitrogen and atomic orbit of oxygen. When they combine, they form the molecular orbit of nitrogen monoxide. Now, the energy level of oxygen is slightly lower. Look at these points. Compare with the nitrogen, slightly higher. For oxygen, for all the orbitals, oxygen, the energy level is lower than that of the nitrogen. So nitrogen is having 7 electrons, its atomic number, while oxygen, the atomic number is 8. So if we fill in here, they join to form molecular orbitals, one from one side, one from another side, until we come up with the molecular orbital of nitrogen monoxide. And how do we calculate the bond order? We add electrons from the electrons in bonding molecular orbital and then subtract off those from the antibonding molecular orbitals. How many do we have? We have 2 in bonding molecular orbital. We add on 2, which is 4. We add on 2, which is 6, plus another 2, 8, plus another 2, 10. So we have 10 electrons in the bonding molecular orbital. Those ones in the antibonding, we have 2 plus 2, which is 4, plus 1, which is 5. So 10 minus 5, the answer is 5, divided by 2, the bond order is 2.5. So nitrogen molecule exists and it is paramagnetic because we gave a reason that whenever you get an shared electron, that molecule is paramagnetic. So nitrogen monoxide is paramagnetic because of unpaired electrons, and the bond order is 2.5. Let us look at hydrogen fluoride molecule. In the formation of hydrogen fluoride molecule, only the 2px orbital of fluorine atom overlaps effectively with the s orbital of hydrogen, resulting in the formation of only 1 sigma sp bonding molecular orbital and the corresponding sigma antibonding sp bonding molecular orbital. The 2px and the 2py orbital of fluorine do not overlap with the s orbital of hydrogen. Let us look at the molecular orbital diagram. It looks like this. We only use the electrons in the 2 orbital. We have a 2 s2, 2p, 5. So the electrons from the 2s, they come in front here to form, in the middle to form the molecular orbital. Then the 2p, the 2 shared the 2 lone pairs, or the 2 lone pairs in each orbital do not participate in bonding. They are called non-bonding molecular orbital, but the one which is not shared overlaps with the 1s of hydrogen to form the sigma sp bonding molecular orbital. And there is nothing in the sigma antibonding molecular orbital. Therefore, the bond order will be calculated using these 2, which is 2 minus 0 over 2, and the answer is 1. Therefore, hydrogen fluoride exists. It has a single bond, and it is diamagnetic because of the presence of the paired electrons. When you look at the molecular orbital diagram, it has paired electrons in the sigma molecular orbital. As an assignment, draw the molecular orbital diagram of carbon monoxide and hydrogen chloride. Calculate the bond order and comment on their existence, number of bonds, and magnetic properties. Next time, we are going to look at metallic bond.